Today in this module, we are going to talk about bioremediation. We all know that Earth is a beautiful place to live in, with beautiful nature around. But in course of time, because of construction sites, industrialization, advancement in technologies, and basically because of human interference, nature is getting polluted. Now to eradicate this pollution, bioremediation comes into picture. Bioremediation is a waste management technique which involves the use of biological organisms to remove or neutralize the pollutants from a contaminated site. So in this module, we will be learning what is bioremediation, the types of bioremediation, its advances and the disadvantages of bioremediation. Bioremediation is a waste management technique that involves the use of organisms to remove or neutralize pollutants from a contaminated site. Bioremediation is a treatment that uses naturally occurring organisms to break down hazardous substances into less toxic or non-toxic substances. Technologies can be generally classified as in situ or ex situ. In situ bioremediation involves treating the contaminated material at the site, while ex situ involves the removal of contaminated material to be treated elsewhere. Recent advancements have also proven successful via the addition of matched microbe strains to the medium to enhance the resident microbe population's ability to break down contaminants. Microorganisms used to perform the function of bioremediation are known as bioremediators. Bioremediation can occur on its own in nature or can be spurred via addition of fertilizers for the enhancement of bioavailability within the medium. Bioventing, bioleaching, bioreactor, bioaugmentation, composting, biostimulation, land farming, phytoremediation and rhizofiltration are all examples of bioremediation technologies. On the basis of removal and transportation of waste, bioremediation technology can be classified as in situ and ex situ. In situ bioremediation involves treatment of contaminated material at the same site, while ex situ involves complete removal of the contaminant material from one site and its transfer to another site, where it has been treated using biological agents. In the comparison of both methods, it was found that the rate of biodegradation and consistency of process outcome differs between in situ and ex situ methods. With the need for excavation of contaminated samples for treatment, the cost of ex situ bioremediation is relatively high as compared to in situ. In situ and ex situ, both the bioremediation methods depends essentially on microbial metabolism. However, so far in situ methods are preferred over ex situ for ecological restoration of contaminated soil, water and environment. Types of bioremediation. Phytoremediation. The three main steps in inorganic ion transport in the simplest pathways are active transport of metals across root membranes, entry of metals into symplast during translocation from root to shoot, and chelation and sequestration of metals into specific compartments in the leaves. Phytoremediation, the use of plants to remove or degrade contamination from soils and surface waters, has been proposed as a cheap, sustainable, effective and environmentally friendly alternative to conventional remediation technologies. Plants use solar energy to extract chemicals from the soil and to deposit them in the above ground part of their bodies or to convert them to a less toxic form. These plants can then be harvested and treated, removing the pollutants. An ideal phytoremediation remediator would have high tolerance to the pollutant, the ability to either degrade or concentrate the contaminant at high levels in the biomass, extensive root systems, the capacity to absorb large amounts of water from the soil, and fast growth rates and high levels of biomass. Phytoremediation of heavy metals from the environment serves as an excellent example of the process of plant facilitated bioremediation and its role in removing environmental stress. The ideal type of phytoremediator is a species that creates a large biomass, grows quickly and has extensive root system and must be easily cultivated and harvested. For example, the plants like Thalaspi and Brassica gentiana. Now, let us talk about the mechanism of phytoremediation. The entry of heavy metals into the plant system is a complex process and involves both the apoplastic and symplastic pathways. We had talked about the three main steps in inorganic ion transport in the symplastic pathways, that is the active transport of metals across the root membranes, entry of metals into symplast during translocation from root to shoot, and chelation and sequestration of metals into specific compartments in the leaves. Chelation of metals within the plant allows the xylem loading and transport as well as for sequestration. These mechanisms involve many metal specific chelators, that is ligands and organic acids, many of which have only begun to be studied or have not yet been characterized. The role of chelators in hyperaccumulation is to form complexes with heavy ions. This can serve the function of aiding in transport, or it can be the terminus of the ion leading to sequestration in the shoot of the plant. Metallothioneins and phytochelatins are two classes of chelators involved in metal accumulation. Different organic acids and ligands have been found associated with various metals in distinct parts of different plants. For example, in Thalaspi, most zinc in roots was associated with histidine, while in shoots it was associated with organic acids. In Thalaspi, cadmium in the leaves was found to be bound with sulfur ligands. In Arabidopsis, zinc was mostly stored in the vacuoles of mesophils, while in Thalaspi it was in the vacuoles of epidermal cells. There are several drawbacks and the advantages of phytoremediations. There are several advantages of phytoextraction. The cost of phytoextraction is fairly low when compared to conventional methods. Another benefit is that contaminant is permanently removed from the soil. In addition, the amount of waste material that must be disposed of is substantially decreased, and in some cases the contaminant can be recycled from the contaminated plant biomass. The use of hyperaccumulator species is limited by slow growth, shallow root system and small biomass production. There are several factors limiting the extent of metal phytoextraction, including metal bioavailability within the rhizosphere, rate of metal uptake by roots, proportion of metals within the roots, rate of xylem, loading and translocation to shoots, cellular tolerance to toxic metals. The drawbacks of phytoremediation. Depending on the growing conditions required by the plant, the phytoremediation process is dependent on it. Tolerance of the plant to the pollutant affect the success for remediation. Contaminants collected in senescing tissues may be released back into the environment in certain seasons. Time taken to remediate sites far exceeds that of other technologies. Contaminant solubility may be increased, leading to greater environmental damage, and the possibility of leaching may occur. Next, we will be talking about mycoremediation. Remediation through fungi is also called mycoremediation. Mycoremediation tools refer to the mushrooms and their enzymes due to having ability to degrade a wide variety of environmentally persistent pollutants, transform industrial and agro-industrial waste into products. The mushroom and other fungi possesses enzymatic machinery for the degradation of waste or pollutants and can be applied for a wide variety of pollutants. However, mushrooms, Basidiomycetes fungi, are becoming more popular nowadays for remediation purposes because it is not only a remediation tool, but also provide mycelium or fruiting bodies as a source of protein. Fungi breaks down most contaminants into non-toxic byproducts, but just act like dynamic accumulators with heavy metals. Oyster mushrooms are also powerful absorbers of mercury and cadmium. Their mycelium channels mercury from the grouped up into the mushroom itself. Enzymes from the fungal mycelia are able to cleave certain atoms like chlorine of larger molecules and then break the bond between hydrogen and carbon. Bacteria can help to further degrade these compounds into final products including carbon dioxide, water and potentially methane. Fungi have also proven useful in remediation of heavy metals such as lead and cadmium. These metals are already at their simplest state and are not degraded further. Fungi can extract them from the soil or water and accumulate them in their tissues. Mushroom fruit bodies attracted innumerable flies and insects, and the previously contaminated soil became its own life sustaining habitat. In the slide, we can see the plant species and fungal spores used in the bioremediation process of the heavy metals. In this slide, we can see that the mushroom species are able to degrade polymers such as plastics. The biodegradation mechanism is very complex. The reason is the influence of other biochemical systems and interactions of ligninolytic enzymes with cytochrome P450 monooxygenase system, hydroxyl radicals and the level of hydrogen peroxide which was produced by the mushroom. So, this table shows the role of mushroom in degradation of pollutants. This table shows the plant species and fungal spores which are used in the bioremediation process of the heavy metals. Heavy metals like cadmium, nickel, zinc, lead, cadmium, copper can be bioremediated with the help of these plant species and fungus. The removal of metals or pollutants from the environment by bacteria is called biosorption. Biosorption is considered as an alternative to the remediation of industrial effluents as well as the recovery of metals present in effluent. Biosorption is a process based on the sorption of metallic ions or pollutants from effluent by live or dried biomass, which often exhibits a marked tolerance towards metals and other adverse impact. Biosorption can be defined as the ability of biological materials to accumulate heavy metals from wastewater through metabolically mediated or physiochemically pathways of uptake. The idea of using biomass as a tool in environment cleanup has been around since the early 1990s, when Arden and Lockett discovered certain types of living bacteria cultures were capable of recovering nitrogen and phosphorus from raw sewage when it was mixed in an aeration tank. This discovery became known as the activated sludge process, which is structured around the concept of bioaccumulation and is still widely used in wastewater treatment plants today. It wasn't until the late 1970s when scientists noticed the sequestering characteristic in dead biomass, which resulted in a shift in research from bioaccumulation to biosorption. In this table, we can see the microorganisms used for biosorption of heavy metals. The microorganisms like Bacillus, Pseudomonas, Microglia, Citrobacters and Chlorella, Aspergillus, Pleurotus. These are the common microorganisms which help in bioabsorption of these chemicals like zinc, copper, nickel, lead and mercury. The essential factors for microbial bioremediation are microbial population. The desired conditions are suitable kinds of organisms that can biodegrade all the contaminants. Then oxygen, enough of oxygen should be there to support aerobic biodegradation. Water, soil moisture should be from 50 to 70% of the water holding capacity of the soil. The nutrients like nitrogen, phosphorus, sulfur and other nutrients to support good microbial growth should be there. Optimum temperature, which is almost 0 to 40 degrees centigrade for the growth of microbes, and the pH, the best range is from 6.5 to 7.5. Advantages of bioremediation. Bioremediation is a natural process and is therefore perceived as an acceptable waste treatment process for contaminated material such as soil. Microbes able to degrade the contaminant increase in numbers when the contaminant is present. When the contaminant is degraded, the biodegradative population declines. The residues for the treatment are usually harmless products and include carbon dioxide, water and cell biomass. Bioremediation is useful for the complete destruction of a wide variety of contaminants that are considered hazardous and can be transformed to harmless products. This eliminates the chance of future liability associated with treatment and disposal of contaminated material. Instead of transferring contaminants from one environmental medium to another, for example from land to water or air, the complete destruction of target pollutants is possible. Bioremediation can often be carried out on site, often without causing a major disruption of normal activities. This also eliminates the need to transport quantities of waste off-site and the potential threats to human health and the environment that can rise during transportation. Bioremediation can prove less expensive than other technologies that are used for cleanup of hazardous waste. Last, we will be talking about the disadvantages of bioremediation. Bioremediation is limited to those compounds that are biodegradable only. Not all compounds are susceptible to rapid and complete degradation. Next there are some concerns that the products of biodegradation may be more persistent or toxic than the parent compound. Next is the biological processes are often highly specific. Important site factors required for success includes the presence of metabolically capable microbial populations, suitable environmental growth conditions and appropriate levels of nutrients and contaminants. Research is needed to develop and engineer bioremediation technologies that are appropriate for sites with complex mixtures of contaminants that are also evenly dispersed in the environment. Regulatory uncertainty remains regarding acceptable performance criteria for remediation. There is no accepted definition of clean. Evaluating performance of bioremediation is difficult and there are no acceptable endpoints for bioremediation treatments. To summarize, we can say that bioremediation is a natural process of eradicating the pollutants from contaminated sites. So, it is a less expensive technique and the residues after the bioremediation are less harmful for human mankind. So, it should be extensively used by humans. Thank you.